All right. Okay. Thank you. So I'm Jaiyeola Temitope. I'll be talking on some non-associative hyperalgebraic structures. This is a collaborative work with Ilori and Oyebola. The point of my presentation, the abstract, I'll give an introduction and background of the study. I'll be talking about hypergroup, polygroup, HV group, and some other hyperalgebraic structures. And I'll also talk about quasi-group and loops. And thereafter, we'll go into the main study and the results, the introduction of polyquasi groups, polyloop. We'll look at the establishment of some equivalent, some results on equivalent hyperalgebraic structures. Thereafter, we developed a method for the construction of polyquasi groups and polyloops, and then we were able to get some algebraic properties of a right polyloop, and we're able also to get some examples that fit into our into these properties. In this paper, new algebraic structures called hyperloop, multiloop, polyquasi group, and polyloops. It's a special class called polyloop, of a polyloop called right polyloop, are introduced and studies. It is shown that any non-commutative groupoid, quasi-group, or loop, commutative and non-communicative polygroupoid, polyquasi groups can be constructed. So that is from any given any non-commutative groupoid, quasi-group, or loop, you can construct a commutative and non-commutative polygroupoid and polyquasi group. And it's also shown that the right polyloop is characterized by any of 7 equivalent identities and has the right alternative property. 2 examples of right polyloops were also constructed with the aid of rings. Hypergroup. The notion of hypergroup was introduced by Marty in 1934 at the 8th Congress of Scandinavian mathematicians. AG group are suitable generalizations of groups. We all know that for a group, the composition of 2 elements is an element, while in an hypergroup, the composition of 2 elements is a set. So the motivation example is this particular one, given a group and a subgroup. If you consider that particular quotient set defined as follows, it will become an hypergroup. Have been studied intensively. Some of them are regular hypergroup, reversible regular hypergroups, and so on. And the beauty of the study of hypergroups is that it gives an extreme diversity and complexity with respect to group theory. Here is the definition of some of the hyperalgebraic structures: semi-hypergroup, quasi-hypergroup, hypergroup. So given an hypergroup H naught, okay, that pair will be called an hypergroup. Given a non-empty set H, you call that pair an hypergroup if that hyper operation is defined. And an hypergroupoid is called a semi-hypergroup if it obeys the law of associativity. Also, in addition, if it obeys axiom, then it will be called an hypergroup. Hypergroup, okay, that pair will be called an HV group if it is a quasi-hypergroup and it obeys what we call the weak associative condition, WAS, as shown. Also, if you have an hypergroupoid, it is called a Marty-Mofang hypergroup, HM group, if it's a quasi-hypergroup and it obeys the Mofang identity. Now I go to polygroup. Polygroups were introduced by Davas. A polygroup is a system, okay, in which you have an element E in P, and you have a unary operation Okay, and also an hyperoperation dot that maps P cross P into non-empty subsets of P. So if the following axioms P1, P2, and P3 are obeyed, then you have what we call a polygroup. If you look at those three axioms, P1, P2, and P3 critically, you can achieve the axioms of a group from them. So a polygroup actually generalizes an hypergroup and in fact generalizes a group. An example is the double coset algebra given by Davas. Hyperalgebraic structures have been studied extensively. Several articles and books have been written on them, and they have been found to be applicable in several fields like geometry, codes, cryptography, and so on and so forth. But of interest to us is the work of Idari et al., in which they consider non-associative hyperalgebraic structures, and they were able to discover that some metathesis in chemical systems and even some biological systems can actually be expressed in a hyperalgebraic form. Jaiyeola and Jaiyeola investigated weak associative properties in hyperalgebraic structure. Before I go into the set, if you define a binary operation on it, if it's closed, you call it a groupoid, and you call it a quasi-group if those two equations have unique solution in X and Y for all A, B, C, D in G. A quasi-group is called a loop if there exists a unique element, E, called identity element, which obeys that particular axiom. Bow loops were discovered by Jerry Bow in 1937, and they have been studied extensively. They generalize what we call Mufang loops, and the PhD thesis work of Robinson in 1964 studies Bow loops extensively. Since then, in the 1980s, attention was paid to the construction of finite Bow loops, and several authors have contributed in this respect. Bond, Shulani, and Sharma, and so on. Also, Chain and Goodyear have also contributed to the study of Bow loops in this current millennium. At a particular point in time, the most interesting problem in Bow loops was solved by Nagy, in which he was able to show that there exists a simple Bow loop. And now I move to this definition is the definition of a loop in the universal algebra sense. Now we go to polyquasi groups and polyloops. Now, given a non-empty set with an hyperoperation, okay, that couple is called an hypergroupoid or polygroupoid. And if you have an hypergroupoid, it's called an hyperquasi group if you satisfy the reproduction axiom. If in addition, there's an element E that obeys that particular axiom, then the triple is called an hyperloop. Thus, an associative hyperquasi group is an hypergroup. So our motive actually in this work is to study non-associative hyperalgebraic structures. So we give the definition of a polygroupoid, polyquasi group, and polyloop as follows. Giving a polygroupoid element E with two hyperoperations, if the axioms in A, Roman figure 1, Roman figure 2, and 3 are satisfied, then you call that quadruple a polyquasi group. If in B, if the axiom in B is obeyed in addition, then a polyquasi group is called a polyloop. If the condition in C is obeyed in a polyquasi group, then we call it a multiloop. And if the associative law is obeyed in that quadruple, which is a polyloop, then then it will become an associative polyloop. Ligores introduced Marty-Mufang hypergroup and did some study on some finite cases classification. But here we will be concentrating on the generalization of this, which is Bow polyloop. Our first result is this particular theorem, which gives equivalent hyperalgebraic structures. Given a polygroup, the following are equivalent by group a group hypergroupoid, and what we call a Marty quasi-group as used by Smith. Also, an hyperloop, a triple G dot E is an hyperloop if and only if it is a multi-loop. That pair is an hypergroup if and only if it's an associative polyquasi group, and that same pair is an AG group if and only if it is an associative polyquasi group. If it's a polyquasi group with ones, and that pair will be a Marty-Mofang hypergroup if and only if it is a Mofang polyquasi group, and it will be a polygroup if and only if it's an associative polyloop. We have a corollary to this particular theorem, which says that if G is finite and G dot is a polygroupoid, then the following statements are equivalent. That quadruple is a polyquasi group, and the union of entries in each row and in each column of the multiplication table of G dot is equal to the underlying set, and every element in the underlying set of G is contained in at least one entry in each row and one entry in each column of the multiplication table. So the importance of this particularly is the fact that for your quasi-groups and loops, which are binary systems, you can easily recognize when you see a finite quasi-group or loop, especially when it is expressed in form of a representation loop. Okay, we'll still see that as we go on. Now we go to the construction of polygroupoids, polyquasi-groups, and polyloops. We now describe a method of construction of commutative and non-commutative polyquasi-groups using non-commutative quasi-group. That particular theorem says that if you are given a non-commutative groupoid quasi-group a loop, that if you define an appropriation on it in this particular manner, then there exists left division and right division appropriations such that GOSEC is a commutative polygroupoid. That quadruple is a commutative polyquasi group, while the other quadruple are non-commutative polyquasi group. And item 3, that particular set is a commutative loop. So the proof is as given here. We are giving a quasi group, a non-commutative quasi group, okay, with a non-commutative polygroupoid, the non-commutative groupoid. Using that particular hyper operation, you can show that there exists the right and the left division, which will satisfy the axiom of our polyquasi group. And here are examples. The table 1 there represents a groupoid. Okay, so using that particular theorem, we have a commutative polygroupoid as shown in this particular table. So, like I was saying earlier on, this part, if you look at table 1, you will discover that it's a Latin square. No entry repeats itself in any row or column. So the corollary we got earlier on can be used to determine, to decide, to tell if a multiplication table truly represents a finite polygroupoid or not. And as you can see in this particular table 2, if you take the union of entries in each row and entries in each column, you will see that you are going to get the underlying set G 1 to 6. The second example here is that of a polyquasi group. Okay, and the table 3 represents a non-commutative quasi group, and with it, from each you get its corresponding non-commutative quasi groups under the binary operation left division, and also non-commutative quasi group under the binary operation right division, and thereafter you can get the commutative polyquasi group as given there. Okay, so we go on to the properties of right-bow loops. We now present some results on algebraic properties and cancellation of right-bow loops. Recall that we defined a right-bow polyloop by just one identity. We're able to show here that the following 7 identities equivalently define a right Boole polyloop. Time will not permit us to discuss the proof of this here. And here is an example of a right Boole polyloop. Consider the ring of integers modulo 2. Let G equals to Z2 cube. If you pick any 2 elements in G, define a binary operation on their product in this particular manner. Now consider Z23 / N. N there is the nucleus of that particular structure, and it can be shown to be that. So with this our new quotient set, if you define a new binary operation sec as given in this particular slide, it can be shown that it is very much true that that quotient set under sec is actually a right Boole polyloop. And there's a second one also. We are using the same ring, but we are defining the binary operation in another sense, in another way entirely. Okay, and it can also be shown that if you consider Z2 cube modulo N, where N is the nucleus, by the nucleus we mean the set of those elements which do not associate with all other elements on the right, on the left, are in the middle. So if you have a binary operation in this particular manner, it can be shown that that particular quotient set is under sec is a right Boole polyloop. And so conclusion, polyquasigroups and polyloops were axiomatized to generalize classical quasigroup and loop and polygroup, and then studied. It was shown that a polyquasigroup or polyloop can arise from a non-commutative quasigroup or loop. Examples were constructed to illustrate this. It was found that a right Boole polyloop is characterized by 7 equivalent identities and has the right alternative properties. So in the future, right Boole polyloop will be investigated for power associativity, right inverse property, semi-automorphic inverse property, as well as orthotopic form characterization. New methods of construction of right Boole polyloop from any right Boole loop or movement group will also be further investigated and demonstrated with example. Of course, many of these properties here are actually true in a binary system. In the case of a right Boole loop, so we want to know if they will also be true in right Boole polyloop. Thank you very much. Yeah, my references. Thank you.
Thank you very much for your interesting talk. Does anyone have questions?
You have studied a nucleus of this polyloop. Have you studied kernel of this polyloop?
You said what? Have I studied what?
Kernel
I didn't hear you
collection.
clearly. Okay, nucleus.
Nucleus is
Sorry,
a set
I
of
didn't get you
associative
right.
element, but kernel action. Have you studied kernel action?
Okay, kernel. You mean kernel? Well, we talk about there's the right nucleus, left nucleus, middle nucleus. The nucleus is the intersection of the 3 of them. We also talk about the center of a loop, okay, which is the intersection of the nucleus and the centrum. The centrum is the set of elements that commute with all other elements in that particular loop, in the case of loop.
Course.
But you said kernel, I don't get you. You know, you talk of kernel of a map.
Of course, thank you. Thank you.
All right.
Other questions? So, if there is no any questions, thank you. Thanks to the speaker again.
Thank you so much.